recording, so I don't forget to do that. And that means I need to start the screen share, so I don't forget to do that either. And make sure I'm recording the right screen. Yes, I am. That's always helpful. Okay, so I was trying to get people to talk to me earlier, and I will repeat that request. Does anyone have things that they want to go over from yesterday or the day before, or questions? It's questions like, I have this data in my head, how does this apply to me, would be also welcome. Because the more examples, the better, is the way I see it. And as always, watching the chat window. And the faces. And the thumbs. Not right now. I'll take it.
Yeah, Lisa, I have a quick question.
Okay.
Could you please repeat what is the meaning of the graph we can saw in slide 21 yesterday? Lecture 2.
Lecture 2, slide 21. What is the meaning of the graph? Yes. This one?
Yes, please.
Okay. So this is meant to illustrate what the model for the variance is trying to recreate in terms of the observed data. So this is, the y-axis on this plot is variance. Variance of the outcome at each separate occasion. In this case, we have 6 sessions as occasions. And the black line is showing what happens if you just let each variance be estimated separately as an unstructured model, or what would be called the saturated model in an SEM context. I'm not tracking the covariances because that gets to be messy in a picture, but this is enough. So the point that I was trying to make with this is that in the data, the variance in response time is decreasing over time as a function of practice. People are becoming more homogeneous. And so whatever random effects I put in the model are going to be trying to recreate this pattern of declining variance over time. If I only had a random intercept in the model, then that is saying what is predicted by the blue line, that the variance stays the same across time. And you can tell that it's kind of an average of what would happen if I let each one be separate. So I find this useful didactically. It's not always possible to see what the variance would want to be at each occasion if you don't have balanced data, but this gets a sense of what the random slopes are trying to do. Their job is to introduce heterogeneity of variance and covariance as a function of the specific occasions that each person has. So it's a function of predicted variance and functions of predicted covariance. That's why time can be unbalanced, because you can be anywhere along the function in terms of which occasion you have. Does that help?
Yeah. Yes,
okay.
Yes, thank you.
Sure. And the slide before it is the same concept, but on the mean side, the fixed effects. So if I had no effects of time whatsoever, that would be the prediction from the red line here, just a fixed intercept. And if I let each occasion have its own mean, I wasn't trying to make a function, I just wanted to perfectly recreate the means, then that would be the black line. So this is what the model for the means, the fixed effects related to time, are trying, that's the trend that they're trying to recreate. So I feel that's useful descriptively. Even if you have unbalanced data, I would round times just so I can make a picture like this, because then that guides me to what family of models is potentially going to be most useful. Question from the chat. I'm currently in the process of developing a physical activity intervention. Curious as to your opinion, advice about things to consider while developing this intervention to strengthen the longitudinal analysis later. The intention is to have about 9 occasions with various measures, physical activity time, amount of time sitting. So is this an intervention that's going to be a between groups kind of thing, or a within subjects kind of thing?
Still in the process of kind of figuring that out. I believe it'll be more between groups though currently.
Okay, so if you're going to do it between groups, then your power to detect any effects of that intervention has to do with the number of people. Number of occasions will help, but not as much as number of people. So that'd be one thing to think of. If you were intending to do it within subjects, so like some days they get an intervention and some days they don't, you would have to be willing to accept carryover effects or be willing to argue why they aren't a problem. So it would have to be, I don't know what if the context would be like if you If you intervene on one day, like, do they forget about that the next day? That seems sort of unlikely. So the argument for between versus within that you're probably used to thinking about in terms of design would still hold here. 9 occasions. Where did you come up with 9?
We had some preliminary data from a prior intervention that was successful, with individuals stating that they liked that number of occasions, that 9 sessions were sufficient for them to learn the skills that we were teaching them.
Okay.
Through these health coaching, so that's kind of where the number 9 came from.
Okay. So is it 9 occasions of you doing something with them, or 9 occasions of you measuring something that happened, or both?
Yeah, good question. So to clarify, it'd be 9 sessions of health coaching, so helping them become more physically active, and then there should be at least 4 times of measurement.
Okay. So then in terms of the data to be collected, it's 4, not 9. Okay. Then I would try to think about in terms of when those occasions would be. You want to capture the period of time in which the most change is likely to occur. So if you would think of like change being like rapid initially but then leveling off, then you'd want to collect more occasions that are closer in time during the rapid period. Likewise, if it's something that has a slow burn and then eventually takes off, then you'd want to do the opposite. A lot of folks want to like automatically have equal interval occasions, and that's not necessarily helpful in terms of the trajectory that you're trying to capture. You might also consider deliberately putting people at different occasions of measurement if that's possible, because ultimately, if you have a trajectory and each person fills in part of it, then you have a better trajectory than if just from what you would get from one person's data. In that case, you'd want to be careful to avoid any sort of cohort effects that would differentiate people for other reasons than just which occasions that they have. That's potentially something you could control for, but it would complicate the model. Those are the things that if you have a piecewise design, get a time point in the middle. I've seen that happen many, many times where, like the example I had with the weight loss, where it was like this. If you only have 3 occasions, only one of the slopes can be random, which means you cannot quantify individual differences in change in both. But if you put a spot in the middle of each of the pieces, then you can. The other thing I would think of is in terms of showing relationships between predictors and outcomes. If you want to show concurrent relationships, then they would need to be measured at the same time. If you had, say, like a predictor that was measured at only 2 occasions and an outcome that was measured at 4, then you essentially only have 2 occasions because there's only 2 points of overlap. So if you're trying to come up with economizations in terms of saving time on the participant side, I would be careful about reducing occasions for some things and not others, because that's going to constrain what you can then do with the relationships among those variables.
Thank you so much.
Sure. What'd I forget? Crowdsourcing here. What else should she worry about in planning this in advance, which is the ideal position to be in, as opposed to, here's my data, fix them. Anyone else have ideas or thoughts for her? No? The room's quiet. It's not just you. I'm bombing here too, so. It's day 3. Just for context, by the way, I used to teach week-long workshops every summer for ICPSR where it was 8 to 5, 5 days a week. And that was back before Zoom was really a thing, and so we all had to like go someplace and stay there for the whole week. And I got to tell you, by 2 o'clock in the afternoon every day, everyone was checked out. Like there was not a single person paying attention. They were all like on their computers on Facebook or doing whatever people did in like 2010. But I was contractually obligated to keep talking because we had all agreed that we were going to have this week-long workshop. And oh my goodness, that was the worst. So I know it's a lot. That's the thing about workshops, is that they're great in terms of like, I'm going to be really efficient and I'm going to learn all this stuff and I'm going to put my mind and only have this in my head. But there's only so much that your mind can absorb. And even if you come back the next day, it's like, I don't know about you guys, but there's sort of a hangover that happens. Like if you have a period of really intense cognitive activity, like after I finish a paper or something, like I am crap for the next couple of days. Like my mind is just like tired. So I appreciate, let me go with that. I really appreciate the fact that you all are making time to be here live in whatever modality works for you, because I know how hard it is to try to maintain that focus. And that I take that as a compliment, and I want to encourage whatever will be useful to you in this experience, given that you've made time to be here. So thank you for doing that. I will say that much, rather than complaining because no one's talking. I understand. But I am still contractually obligated to be here. So we're going to be here. That's what we're going to do. All right. What other questions can I answer before we dive into some new stuff? No one?
I have another question, Lisa.
Let's
Sorry.
see. If you wait long enough, someone will talk. Yes, sir.
Okay, but this is in slide 59. I think that yesterday we didn't talk about this. Slide 59.
Yeah, we did not get to the group stuff yesterday.
Yeah, and I would like to know why we are subtracting between minus group. That's weird.
We are not. That is what happens when you try to write text where there's a dash in the equation editor. It's not a minus sign. It's meant to be a regular dash for between group and between person.
Great. Okay.
Yeah, that's just bad formatting for whatever reason. I gave up trying to fix it at some point. But if I wanted to, let me see if I can fix just this much and unequation it. Yeah, then it looks like that, which is worse somehow. So it's not a minus sign, it's a dash. But that does bring up one of the reasons why if I ever read your work, and I will correct your dashes. Like, I am a dash Nazi when it comes to the proper, like, M dash versus N dash versus hyphen versus dash versus minus sign, and this is one of the reasons why, is because it yields ambiguity in certain circumstances. So that's one of my things. Anywho. All right. Shall we jump into lecture 3 then? Does that sound like a plan? And we'll pick up the rest of lecture 2 likely tomorrow. I think it may fit better there because it's like 3-level day is what we'll have tomorrow. I've got lecture 3 open then right here. Can everyone on Zoom see my screen? Just making sure. Okay, good. And everyone can see this screen, so that's good. All right then. So time-varying predictors is where we're at here. And I have the Joy of Time-Varying Predictors. That's my nod to, like, the joy of cooking, which I hate cooking, to be honest with you. I don't cook. I pay money for food to show up on my doorstep in a box. That's what I do, because I don't like to cook, and I'm not good at it. But the Joy of Time-Varying Predictors, this I can get behind. So whether we're talking about a model where people are changing over the long term, systematically, like a growth curve model kind of thing, or whether we're talking about a fluctuation kind of EMA data, either way, after you put in whatever fixed and random effects related to time that you need, the residuals should look like this. So it's the residuals from the growth curves in the case where we needed them, the residuals from just an intercept in the case where we don't. So time is irrelevant at this point forward. All of these models assume that whatever effects of time that you need are there already. But to keep the exposition of this on the simpler side, I am not having time in these models. So we're starting with just an example of pure fluctuation. And then we'll talk about how the model needs to change to address the concept of time and change simultaneously to time-varying predictors. So why this is complicated is because almost all time-varying predictors contain both between-person variation and within-person variation. And each of those sources of variation has the capacity to have a different relationship with the time-varying outcome. So we got to make sure that we've captured all of that variability and those distinct relationships. So for instance, if I have a study where people are measured every day for a week or two, and I might ask questions about your level of stress, perceived stress, we can all agree that some days are worse than others. I would call that within-person fluctuation or variation in stress. But there's also some common tendencies. Some people are going to report more stress on average than other people. Whether it's because it's real stress or whether it's because they have a different response set for what being stressed means, I don't know. But I do know that there will be systematic person mean differences. And so we can quantify and should quantify in the same way that we would for an outcome how much of each kind of variation we have in a predictor. So even though conceptually you might be thinking of a variable as a predictor, we need to think of it as an outcome in reality. So we can compute an intra-class correlation that tells us how much of it is between. So if we have an intra-class correlation greater than 0, that time-varying predictor has some kind of person mean differences at level 2 embedded in it, and therefore it has the chance for those person mean differences to relate to person mean differences of another variable. If the predictor's ICC is less than 1, then it has at least some within-person fluctuation to it, and that within-person variation can in turn relate to the within-person part of another variable. So there's a parallelness to the predictor and for the outcome. The relationships that each of those parts of a time-varying predictor can show may be the same and they may not be. Most of the time, not be. So the slopes could be in the same direction. So for instance, stress and health. It may be the case that people who have more chronic stress on average relative to other people have worse health on average relative to other people. Within persons, it may be the case that when you're more stressed than usual, you feel worse than usual. And both of those things are in the same direction, where stress is bad for you. But it could also be the case that the slopes at each level are in the opposite direction. So if we look at the relationship between exercise and blood pressure, at level 2, between persons, blood pressure is used as an index of health. Low blood pressure means that you have good health. And so people who exercise more tend to have lower blood pressure than people who are more sedentary. But when you're actually exercising, your blood pressure is higher. So within persons and between persons have different relationships between these two variables because conceptually they represent different things at each level. And more to the point, not just different meanings, different scales. In all of these models, all of the slopes that we're estimating are unstandardized. And there's not a quick and easy way to standardize them that's going to be universally applicable, and that's why standardized slopes in multi-level are not a thing. So the only situation in which you would see the same relationship at between person level 2 as at within person level 1 is if both of the variables had the same intra-class correlations on the same scale and the relationships were the same. All three of those things together is not likely. So in longitudinal data, it is almost always going to be the case that you'll have a different relationship between persons than within persons for your time-varying predictors. And for the same reason that we can't just do regular regression on longitudinal outcomes, we can't ignore this problem in longitudinal predictors. It's two different things at a minimum. So there's going to be 3 different kinds of main effect slopes that are potentially available in a time-varying predictor that has variation at between person and within person levels. So I've got 2 of these on here. The third is grayed out because we're going to talk about it subsequently. And I'm again using color to try and keep track of things. So green is going to be level 2 between person, purple is going to be level 1 within person. So at level 2, are people with higher predictor values on average than over time than other people also likely to be higher on the outcome on average than other people? And if so, that between person relationship should reduce the random intercept variance of your outcome. So the key idea here is more than other people on both X and Y. Are those tendencies related? Within persons then, if you have a higher predictor value than usual, and it's usual if it's relative to a mean, than predicted by your growth curve if it's within a growth curve model. So again, think about the residuals bouncing around the line that you give each person. That's the idea. If you have higher predictor than usual, do you have a higher outcome than usual too? And if that is so, then that relationship should reduce the level 1 residual variance of your outcome. So it's 2 different effect sizes, 2 different types of relationships being captured here. Lost my mouse again. So here's what not to do. So Zoomers, every single person's head in the room just popped up at the same time. That was really funny. Here's what not to do. Okay, if you get nothing else out of this entire week, this is it. Because people do this all the time still. I went to, as an invited speaker at a multi-level conference in the Netherlands about a decade ago. And it was a conference full of people specializing in multi-level analysis, and half of them did this. So now that I have everyone's attention, don't do this. The naive way to talk about a time-varying predictor is just to stick it in the level 1 equation, the same place where YTI is, we got time-varying XTI, and call it good. So what you end up with, if you do this, you might center it at a constant. That part actually doesn't matter, other than for the usual reasons. The fixed effect that you end up with for that time-varying predictor's slope is what I refer to as a smushed effect. Because what it represents is both the effect of being higher on X than other people at level 2, and the effect of being higher than usual relative to yourself at level 1 in one slope. The only situation in which it's okay to have one slope is if those 2 slopes are actually the same, and it's not going to happen most of the time. So I call this a smushed effect because I visualize it as sort of 2 things being smushed together, and they're not going to be equally smushed. It's going to be weighted by the relative amount of information at each level. So because we typically have way more occasions than we have persons, the smushed effect is going to be relatively close to the within effect. It's the between effect that's going to be messed up then, because the smushed effect is assuming that between and within effects are the same. And again, just like piles of variance has a better term for it, the proper way to say smushed is you can call it a conflated effect. That's probably my favorite because that's same sort of visual in my head at least. A convergence effect is what it tends to be called in the context of time. So if you've smushed together cross-sectional age differences and longitudinal age changes, then it's an age convergence effect. Or a composite effect is another term that I've seen. I don't like that one as much because it kind of sounds like that would be okay. Now that being said, I write smushed in all my papers because it's my term and I can. But so maybe you write conflated and then you give me a parenthetical because I'm trying to make smushed happen. I couldn't make fetch happen, but I could make smushed happen. Yes, thank you. Thank you.
Can you give a
Yep.
real life example of what that would look like with what's happening here?
If I were predicting some kind of health outcome from time-varying stress, and I just put in time-varying stress, centered it so that 0 meant something, and I fit a single slope for it, then I would say that the effect of being more stressed than other people is the same as the effect of being more stressed than usual.
Okay.
Another way to say this, for those of you who've seen multi-level stuff before, is that we are assuming there's no contextual effect. So that may help bridge the gap. That's coming in like 15 slides or something, that terminology. But that's another way to think about this, is that we're assuming there's no contextual effect. And in longitudinal data, that's just not going to be true. So we don't want this. Graphically, here's the problem. On the y side, we have let the model partition the variability in y into, at a minimum usually, a random intercept variance at level 2 and a within-person residual for the deviations around those person means at level 1. On the x side, we have not done that. So we're letting the between-person part of x, given by the green here, do the same job as the purple part within person at level 1. So only when these 2 arrows in reality are the same number will shortcutting it by fitting one path instead, one slope, be okay. So we don't want to do that. What do we do instead? You got some choices. One of the choices I like a lot more than the other, and I'll explain why. So what we're going to do to start with, so that we can stay in a univariate multi-level modeling context to begin with. So by univariate, I mean we're predicting one outcome conceptually, even though that outcome is measured longitudinally over time. So we're going to take we're going to take the time-varying predictor, and we're going to compute its mean across time. And that person mean, I'm calling it person mean x here in the notation, is going into the model as a new predictor. So we're literally taking the part of the variable that is between person mean differences, saving it as a new variable, and putting that in the model. And just like any other time invariant predictor, which is what that part is, we want to center it so that 0 means something, so that the intercept stays meaningful. Now what we do at level 1 has 18 different names. It's yet another instance in which people came up with the same ideas and came up with their own terminology. So the one that I like best for longitudinal data in clustered data is called group mean centering, or within cluster centering or cluster mean centering. In this context, we'll call it person mean centering. What we're going to do, I'll show the notation in just a second, is subtract a variable, the person's mean, from the level 1 observed time-varying predictor and put that in the model instead. So I tend to shortcut all of these different permutations of the name with just variable centering, because the key idea is that we are subtracting a variable and not a constant. The other option is often called grand mean centering or constant centering or something along those lines, because you're subtracting a constant. And I call it constant centering because the grand mean is one choice. You could also leave it uncentered, which is the same thing as saying, I'm going to center it at 0. It ultimately doesn't matter. For what we're talking about here, this idea of splitting up between person and within person predictor variance, what constant you pick is irrelevant to that. The tricky part of this is that we will stumble into situations in which, even with a different version of the level 1 predictor, it has the same effect. But at level 2, it's the same predictor, and it carries a different effect in each case. It's very confusing at first. And I will show you both, and I will show you why, and then we'll talk about what all of it means. So here's the first option, the one that I prefer for longitudinal data, person mean centering. So we're going to compute the person mean of x as indicated by x bar here, subtract a constant so that 0 is meaningful, don't care which one it is. And so the variable that goes into the model then is this centered person mean. So PMXI is the shortcut notation I'm using for that. So if the constant that we chose for this was the sample mean, then people who had positive values on this PMX variable would be higher than other people, and people with negative values would be lower. So not different than what you're used to thinking about and what we did yesterday with time-invariant predictors. Level 1 then, I take my original time-varying XTI and I subtract the uncentered person mean. Not the centered version, because then I'd be moving the intercept twice. So then what 0 means is that you're at your own mean, whatever that is. Whatever that is up here in level 2. So a positive value for my new within person x means that I'm above my own average. A negative value means that I'm below my own average. And I'm going to shortcut that as more than usual or less than usual. So x bar I, that's the variable that's being subtracted here. So what is happening then is that we are literally carving up the time-varying x into its between person mean differences part and its within person around the mean part. And we're putting those two new pieces of it into the model instead. So XTI is gone. It's been replaced by the pieces. So here's what it would look like in an equation with no other predictors. Again, for simplicity, you can have other predictors and stuff, but this is enough. So to remind us what each of the variables mean, I've got their definitions over here. So they both go in. At level 1, I have a fixed slope that goes with within person x for now. Because I have pulled all of the between-person variation in the predictor out of it, it only has within-person variation left. The slope can only be the within-person effect. So we've kind of experimentally controlled these variables, right, by pulling the pieces apart ourselves. So gamma 1O is the effect of having more x than usual. For every unit more x you have than usual, this happens to y at that same occasion. So this is within-person longitudinal information, but we're estimating a concurrent prediction to start with. The other slope then, gamma O1, is the between-person effect, because person mean x only has level 2 person mean variation. That's the only kind of slope it can have, is a between-person slope. So this tells us about the effect of having more x on average than other people. So for every unit more person mean x, then gamma O1 describes the change in the average outcome over time. More than other people, level 2, more than usual, level 1. And because each of these variables is going to be uncorrelated with each other, their slopes stay the same regardless of whether the other one's included. So that's why I like this, because you can't screw this up. You set up your variables ahead of time so that you know what they mean. You put them each in. You put one in, it's the within. Put the other in, it's the between. The end. So graphically, what we've done is take x and split it up into two new boxes. And I'm using boxes to denote that these are observed variables, where I've got person mean x up here, carrying the level 2 between effect. I've got within-person deviation x at level 1, carrying the within effect. So now there's a symmetry with what's happening on the outcome side with respect to piles of variance being carved up in each of these things. And now you might be looking at this and going, wait a minute, why do we have circles on one side and boxes on the other? That seems kind of arbitrary. And yeah, it is. So circles is the idea of model estimated variance components. The centering process that we used is the brute force way to accomplish that same thing. So person mean x is meant to represent the random intercept of x. Within person level 1 x is meant to represent the level 1 residual variance of x. And towards the end of this lecture, we will turn these into circles instead. And then we will have done what I call multivariate multi-level, because now we have two different outcomes whose variances are being partitioned, and what the rest of the world calls multi-level structural equation modeling. The reason to do it this way is entirely based on software, because the model only has one outcome. So we can't tell it to partition the variance of x and then have x predict y. We could hack univariate software to make circles for both of them, but then the only way to let them be related is to have covariances instead of slopes. And that limits the kinds of questions that you can ask. So for now, boxes. All right. How are we doing so far? Tentative nods in the room, Zoomers. Thumbs sideways, thumbs up. A few thumbs up. There's no poop emojis yet, so I suppose that's good. That's for thumbs down. Or angry face emojis. Okay, any that you want to hear again, differently? I do have an example coming in a couple slides. Okay, so what could happen then with respect to each of these types of slopes? I've got some hypothetical scenarios here. So let's say that I have time-varying stress and time-varying severity. So in contrast to almost all the other pictures I've shown, this x-axis is not time, it's stress. Time has already been either in the model if it needs to be or not in the model if it doesn't need to be. And what I have here are different lines for different people. So I have my red person who has a mean stress of 4, and sometimes they're lower and sometimes they're higher. My green person who has a mean of 5, and my blue person who has a mean of 6. And the yellow line through their means then conveys the between person slope. For every unit more mean stress on average, severity goes up by 1. The slope of the yellow line is 1.
Severity is time invariant?
Nope, it's time varying.
Oh, okay. But it just stays the same.
The prediction stays the same because the within slope is 0.
Oh, okay.
So yeah, so these are like hypothetical extreme scenarios. The within slope of each of these lines is 0. So what that means is that how much more stressed you are than usual has no effect on your severity. All of the action is between persons, and if you had these data and you went to the trouble to collect longitudinal data, you're likely to be very disappointed. Because this same yellow slope, you could have gotten from one occasion. It's between persons, it's a cross-sectional relationship. Now maybe you can spin it that it's noteworthy and theoretically informative that I got a null effect within persons, and good luck to you spinning that into a paper. It can be done, just it's a little tricky. But it would be a bummer, because that means basically you got the same answer whether you measure them once or 5 times. Arguably, the person mean is more reliable than a single measurement, so you'd get a better estimate of the relationship, but it's still, in this picture, entirely within persons. Now, here's the opposite. Camera 1, camera 2. Camera 1, camera 2. That's a Wayne's World reference. Another thing you should head to the YouTube to learn about if you're not familiar. In this case, the person who went to the trouble to collect longitudinal data is going to be very excited, because now we have a relationship that is entirely within persons. For every unit more stress you have than your mean, whatever that is, your severity at that occasion is higher than usual by 1. The slope of the between person relationship through the means is 0. It's not that people who have more stress have more severity. It's that when you have more stress than usual, you have more severity than usual. Or you could have both. So in this case, I have 2 positive slopes of different magnitudes. The yellow line slope is 2. So for every unit more stress on average than other people, severity on average goes up by 2. Within persons, for every unit more stress than usual, severity at that occasion goes up by 1. And you can have all different combinations of these things, but these are just a few examples that are easy to draw. So here's a story / example. It's a true story. So this is example 5 by my count. These are data that were collected by a friend of mine when I was a graduate student, and I was an analyst / research assistant helping to manage the study and analyze the data. And the context of the study is a dermatology clinic where there were access to 127 patients undergoing treatment for psoriasis, which is a skin condition that's thought to be exacerbated by stress and other kinds of environmental factors. And when my friend proposed her dissertation to look at the relationship between stress and coping and psoriasis, she walked into her dissertation proposal meeting with a happy little cross-sectional design, like everyone else did in positive psychology. Let's go with, today I'm a positive psychologist. And by the time she walked out of that defense, they had convinced her into adding a longitudinal second half of her dissertation study. So she did, because she wanted to have the done kind of dissertation. So every week over the summer for 8 weeks, we mailed out a packet of questionnaires, and some of the people sent the questionnaires back, and we had a whole bunch of different items, but of interest here is an index of psoriasis severity and an index of their perceived stress. So this is a graph that shows severity over time. And this is not a treatment study. This is just an observational, oh, by the way, can you fill out these extra papers? Cool, thanks. So there's no effect of treatment or time. And initially, thinking about these sorts of data and how I would get stress to predict severity, this really threw me. So I don't even remember what I came up with as a graduate student because I know it was 17 kinds of wrong in retrospect. But I got to Penn State, where I had a lot of smart methodologists that I had access to, and they had this thing called Methods Lunch, which I'd like to bring back here, by the way, if anyone's interested. What it was literally all of the methodologists, like across several departments, would bring a lunch. We'd sit in the room, and whoever wanted free consulting advice would come and present. And they got the advice of all of us at the same time, and most of the time we argued with each other as to what should happen, and that was fun and very informative. And the grad students took it and got a course credit for listening to the debate and sometimes joining in. And initially, when I started going to this, I was like, well, it's longitudinal, but like I don't think a growth curve model, because it's not growing. And like, how do I do this if it's not a growth curve? And Mike Rovine raised his hand. He's like, just don't put time in. What? Just don't put time in. Just do a multi-level model, put stress in, don't put time in. It's like, you can do that? Yeah, you can do that. So that's what I ended up doing eventually. So the questions then to go through the process, all the steps that I'm skipping, as we discussed yesterday. ICCs for stress and severity is the first pass. Do I have longitudinal data and how much of each kind? Then, given that I'm trying to predict severity, I want to assess its pattern of variance and covariance so I can get the right time model with respect to the model for the variance, not necessarily the model for the means. And then try to figure out whether or not there is a relationship between stress and severity, but the reason they wanted to do the study was to look at the lag. So if you have a crappy week, how long does it take before that shows up in your skin somehow, is essentially the question. And there are a lot of longitudinal studies who want to look at these sorts of lagged relationships, especially reciprocally across variables. So this is an instance in which the hypothesis was going one way and not the other, but we'll have examples of both coming up later on. So we're thinking of stress as the predictor, severity as the outcome. So step one then, empty means random intercept models to get intra-class correlations out of both of these measures. So to remind us what the empty model looks like in condensed form, it's right here. Each variable gets a fixed intercept, a random intercept, and a residual at each occasion. We estimate the variance across people in those random intercepts at level 2 to capture person mean differences. We estimate the variance of the level 1 residuals across time and persons, constraining that to be equal to start with. And we feed those into this intra-class correlation formula, where the numerator is between person mean differences. So for severity, the intra-class correlation was 0.83. So that means that her dissertation committee gave her an 83% waste of time as an extra task. Now, why am I saying it that way? Oh, a few people want to join Methods Lunch. Excellent. We'll get that going. Why am I saying that this is an 83% waste of time? Any guesses? What's 0.83 mean?
The percentage of between person variance.
Yep, percentage that's between person, percentage that's due to mean differences, percentage that is cross-sectional, which she already did. So she has 17% of the information in this variable is possible to be predicted with time-varying stress, only 17%. So it looks like, and as you might guess from the picture, some people have worse severity than others, and that doesn't change all that much. Bummer for them. On the good news, I guess, stress had an intra-class correlation of 0.56, so roughly half and half. After a 20-page handout, and no, I'm not exaggerating, those of you who've been through my classes know the handouts kill many trees. About 20 pages later, going through the process of trying to figure out what the pattern of variance and covariance looks like if I fit an unstructured model and trying to come up with something that recreates that more parsimoniously, I ended up with a hybrid approach where I put in a random intercept. So the fact that I have an average correlation over time of 0.83 means that person mean differences is going to have to be part of the story. There's just no way around that. So I put in an intercept. And then the question is, what is the pattern of variance and covariance of the residuals that remain? So after I control for person mean differences, what's left in the R matrix? And after a series of model testing things, we ended up with this one. So this is showing a correlation matrix of the level 1 residuals for weeks 2 through 8 of the study, which are actually labeled 1 through 7 here. And the structure that I ended up with, the best fit that was not worse than the best model, is what's known as a toplet structure, or banded, and up to lag 3. So if you look at the off diagonals here, the correlation between the residuals for the first occasion and the second occasion and the third and the fourth, and so on, is 0.5. So after controlling for person mean differences, your severity last week and your severity this week are correlated according to this model 0.5. The model estimates a separate lag 2 correlation, so first and third, second and fourth, third and fifth, etc., of 0.35. So in a toplet structure, there's no requirement that these correlations are related to each other. They're each estimated separately. And then one more was needed for a 3-week lag, so that's why it's lag 3, of a correlation of 0.1. And after that, these were significant or non-significant. They were close enough to 0 that we don't have to have them. Turns out, though, while SAS had no problem fitting this model, I had a very hard time trying to find other software that could do it. So, including R. So that's where that table came from, a SAS output. So here's what the model then would look like, again, skipping a series of steps building up to this point, that would answer the primary question. So I have 2 level 1 predictors that I'm calling within person stress at lag 0 and lag 1. And each of these was created by subtracting the person's mean. So I had to lag the data, as it's called, by taking shifting everything down 1 row so that last week's stress is on the same line as this week's severity. And then I person mean centered both of them. So there are routines to do this, by the way, in most packages. You can ask it to help you shift your data. The trick is not to lag the last occasion of the first person into the next occasion of the second person. That's the catch. And because I knew that I wanted to look at lag 1, that is why I only had weeks 2 through 8 in the model. Because last week's week 1 stress can predict week 2 severity, but then week 1 severity isn't predicted by anything. So those rows would be incomplete and would get deleted. So that's one significant drawback of this kind of approach, is that you have to drop the occasions that don't have the lagged predictors before them out of the model. So weeks 2 through 8 is what we're looking at here. Then at level 2, I have a main effect of person mean stress, and I centered it near the mean of that variable, which was a 2. So now I have my fixed intercept is going to tell me the expected outcome when all the predictors are 0, just like usual. Here, that's the expected severity this week for someone whose person mean stress is a 2, and someone whose severity was added to last week and this week, because that's when these within person variables are at 0, is when you're at your mean. So note that it's just last week and this week. It's not week 1 versus week 2 versus week 3, because time is irrelevant. This is not a growth curve. And Mike Rovine said it was okay just to leave time out. And he knows more than me. So I'll trust him. So gamma 00 then, our baseline. Gamma 01, that's my between person slope. So it's going to be the difference in average severity per unit person mean stress. So this answers the question cross-sectionally, do people who have higher stress on average have worse severity on average? And then the 2 within person effects, for every unit more stress than your mean, each of those is the change in severity that week for lag 0 and next week for lag 1. And here's the results. Most of the story is between persons. So the coefficient for the effective person mean stress is 0.48. The coefficients for the lagged effective stress are much smaller, although lag 1 was actually significantly different than 0. And to remind you, these are all unstandardized. So to interpret what they mean, I have to know what a unit is. and all of the units are the same and that it's 1 unit more stress, but it's then average for this coefficient and then usual for these. And so I made a picture to illustrate this where I have the x-axis is within person stress the previous week, and then I have relatively low values, average values, which would be when you're at your person mean, and then above average. And these are different lines for different people. So the between person effect is indicated by the difference vertically across these 3 lines. People with higher overall stress have worse overall severity. The slope of each of these lines then is the lag 1 fixed effect of 0.06. So for every unit more stress than usual, your severity goes up a tiny little bit. Okay. Question? No? I'm hearing things. How about that? Questions then. I'm not hearing things. I'm going to ask things. So these lines are parallel. Coincidence or consequence?
Since you only have 3 data points, right?
I have 7 data points, but I'm showing
you're only
sort of within person, low, medium, high
Yeah,
as just a graphical tool. What would it take to make the lines not parallel?
More within person differences.
Keep talking. Heading in the right direction.
Less between person differences? I don't know.
Well, we can't control what's in the data, right? It is what it is. But the prediction that the model's making is parallel lines. And so the question is that a coincidence that it happened that way, or is it a consequence of the model? And while you're thinking of that question in the chat, how do we know that we need 2 within-person stress slopes? Good question. So this is my 2 cents, my opinion, and people will disagree with me. When I think about this idea of a lagged effect, to me, it is only useful after you control for a concurrent effect. So if you want to really say that it's last week that matters and not this week, control for this week and show me that last week predicts incrementally. That's my perspective. But in the models where we're looking at lagged prediction in 2 different directions, most of the time those estimate the same occasion relationship as a covariance instead. They don't control for the same occasion. And that bothers me. But in this model, I got to set it up so that I had the 2. So that's why there's 2. In theory, given that this one is not significant, I could take it out if I wanted to make the model more parsimonious. But if I want to have it as part of my story, that it's not this week, it's last week, then I leave it in because that makes the story. Okay, so coincidence or consequence? Consequence. These are main effects, 3 of them. One of them's not in the picture. The one that's not significant here is not in the picture. But these are main effects without interaction terms. Could I have an interaction term in this model between the layers of stress? Sure, I could. Do you think that the effect of being more stressed than usual depends on how much absolute stress you have? Could. Like if you think about different people you know, or if I think about like undergraduates versus graduate students and grown-ups, it's like when you don't have a lot of stress, like every little thing's a big deal. But then at some point you're like, fine, whatever. I'm already tired and freaked out. Like, what's some more? It's fine. Like stress matters less the more you get of it. That kind of idea. Sure, I could put in cross-level interactions where this blue box is here, potentially of between stress multiplied by within stress, which would allow the effect of more stress than usual depend on how much you have. I also don't have random slopes here that I could have put in. They wouldn't show up in the picture because these types of pictures are typically focused on the fixed effects, but they would change the inference of the fixed effects. So what would a random effect mean in this case of lagged stress? Conceptually. Random means everybody gets their own, right? So what would that translate to if I gave lagged one with in-person stress a random slope, for instance? And Zoomers, you can play along too. I'm watching the chat, or you can talk to me. Your choice. All cameras off, all heads down. Okay, Ahmed, you're looking at me. I'm gonna cold call on you.
So, on average, is the random?
Yeah, what would a random slope for within-person lagged one stress tell us? We got a vote from the chat. Everyone changes with different stress levels. Close, very close, but not quite. And keep in mind, this is the effect of stress that we're talking about. The relationship between lag 1 stress and this week's severity as a slope, just like a time slope, but this is a stress slope. Okay, I'll tell you. No, you were going to answer? Go for it.
The average effect of stress then varies across all individuals?
Yeah, the effect of having worse stress than usual varies across people. The extent to which stress affects your severity shows individual differences. Some people are more impacted by stress than other people. That's what that would mean. So it's not a random slope for change over time, it's a random slope for change over stress. Yep, the fluctuation of stress has different effects per person. Exactly. Exactly. And I can answer whether or not that's needed with the likelihood ratio test, the same as any other variance component or addition to the model for the variance. So I don't have a cross-level interaction between the layers of stress because I don't have a random slope. I would need to test the random slope first because conceptually that's what the cross-level interaction would be trying to explain. So you can see why this stuff gets kind of complicated, right? I have what is essentially a bivariate model here. I got one predictor and one outcome, and I've already done all of this to it. And I'm talking about all the other things that can happen. And here's how I did it in the code. Sort of. So in SAS, this is where this came from. You can fit random effects controlling the G matrix, and you can control the R matrix and have a whole bunch of different structures. So this one is heterogeneous topolits, meaning separate residual variances at each occasion is the heterogeneous part. The 4 has to do with the order of coefficients in the matrix, where the first one is the variances and then the lag 3 are the next ones. That is built into Stata, except it's called topolits 3 instead of 4 because they name it differently, you know, just because. Right? Because why would it need to be the same? And it is not built into SPSS to have a custom topolit structure, although you can have a full order topolits. And in theory, it's possible in R, but I ran out of time trying to figure it out. So that's my, I got to punt on this one. I'll figure that out next time. I know that in Elmer, it's not possible. But Elmer is necessary to get correct denominator degrees of freedom. In LME, it should be possible, but it's not one of the built-in structures. And so I'd have to write some sort of custom thing, and I'm not good enough to do that yet. But we'll work on that. All right. How are we doing? Some nods. Zoomers, are we hanging in there? Any that you want to hear again or hear differently? Okay, so I'm at a pause here in terms of my organization. Should we take an early break or should we push forward? Any votes? Voting for early break? Okay, it's unanimous then amongst the people who voted. Let's see, it's 10:05, maybe 10:20-ish. Come back. All right, I will see you all in about 15 minutes then. And I will hang out here for a few minutes if anyone wants to talk to me.